Have you ever wondered how a machine can actually learn to think? Well, today we're going to pull back the curtain and do exactly that. We are going to build a simple digital brain right from scratch, and we're going to teach it to do something that feels incredibly human, to read our own handwriting.
So here's our game plan. We've broken this down into 5 simple steps. First, we'll define the problem we're trying to solve. Then we'll grab our digital tools. After that, we'll design the brain's blueprint, teach it how to learn from its own mistakes, and finally, the best part, we'll put our new creation to the test.
So, what's our mission here? Well, it's a challenge that seems almost trivial to us, but for a computer, it's actually incredibly complex. We want it to look at a messy, handwritten scrawl and know with total certainty what number it's supposed to be.
You and I can look at a handwritten number and, we just know what it is, almost instantly. But how do we give a computer that same kind of intuition? That is the fundamental question we're trying to answer today.
Now, to learn any new skill, you need study material, right? Well, for our digital brain, that material is the legendary MNS dataset. It's this massive library of digits written by thousands of different people. We'll use 60,000 of them as a kind of textbook for the network to study, and then we'll keep a separate stack of 10,000 hidden away for the final exam.
All right, so how do we actually start building this thing? Every project needs the right tools, and for what we're doing, we really only need 3 key ingredients.
First up, we've got TensorFlow. This is Google's amazing open source library that's basically the powerhouse behind the whole operation. Next, we have our data, which are all these tiny 28 by 28 pixel black and white images. And finally, before we do anything else, we have to do a really crucial prep step. We normalize the pixel values. All that means is we take the brightness scale, which goes from 0 to 255, and we just squish it down to a simple range of 0 to 1. This little trick makes it way easier for the network to learn efficiently.
And now for the really fun part, the architecture. We're not just, throwing random code at a problem here. We're actually designing a blueprint for a brain, building it up layer by logical layer.
So this shows you the entire journey the data takes. First things first, we can't feed the network a 2D grid of pixels. It wants a simple flat list. So we flatten that 28 by 28 image into one long line of 784 numbers. That list then feeds into our first hidden layer. Think of its 128 neurons as tiny detectives, each one trained to spot super basic patterns, things like a straight line or a simple curve. Then, the second hidden layer takes those simple patterns and starts combining them into more complex shapes, like the loop of a 9 or the corner of a 7. And finally, we hit the output layer. It has exactly 10 neurons, one for each digit from 0 to 9, and its job is to make the final call, to spit out a probability for each possible answer.
Okay, so we've got the blueprint, but how does this brain actually learn anything? Well, it turns out it's a process of trial, error, and slow, steady improvement, kind of like how we learn.
And this is the absolute key to everything. For the network to get any smarter, it needs feedback. It has to have a way of knowing not just that it made a mistake, but how big of a mistake it was.
Look at this. This is fascinating. This is a peek inside the network's thought process. It's looking at an image of a 3, but it's only like 40% confident. It thinks there's a small chance it could be a 2, maybe even a 0. I mean, that's not a very good guess, and we need a way to tell the network, hey, you need to do better. And that's where this thing called a loss function comes in. Just think of it like a teacher with a red pen. It takes the network's guess, it compares it to the real answer, and it calculates a score. The higher that score, the more wrong the guess was. Simple as that. And that brings us to the entire goal of training. It's really just one big game of tweaking all the network's internal connections over and over and over with one single objective: get that loss score as low as you possibly can. So here's our specific training recipe. To actually make those tweaks, we use a really popular optimizer called Atom. It's just a smart algorithm for getting that loss score down efficiently. For our loss function, we're using something called sparse categorical cross-entropy, which is a mouthful, I know, but it's just a really good way to measure the error for this kind of problem. We'll track our progress with simple accuracy, and we're going to make the network read through the entire training set 5 full times. Each pass is called an epoch. The training is done, our brain has studied, and now it's time for the final exam. We are about to show it those 10,000 images it has never ever seen before, and find out if it can actually read.
Okay, let's just peek at a single test case. The network is shown a handwritten 7 for the first time. And the result? Wow, look at that. It's not just correct, it's overwhelmingly confident.
It's giving a 99% probability to the right answer. That is exactly what we want to see.
One right answer is great, but it doesn't prove anything. The real test, the moment of truth, is its performance across that entire unseen test set. This is it.
And here it is, an accuracy of nearly 98%. That is absolutely fantastic. It means our simple, four-layer network that we just designed, it correctly identified almost every single one of those 10,000 handwritten digits it had never encountered before.
So let's just stop and think about what we just did here. With just a few key ingredients and a logical design, we built a system from the ground up that taught itself how to read. It's an incredible achievement, and it really opens up a world of possibilities. I mean, if we can teach a machine to recognize numbers this well, what other complex human problems are we going to teach it to solve next?